Hello, everyone. Thank you for attending today's webinar. My name is Shuo Liang. I'm working as application scientist in diagnostic membrane at Sartorius. And in this presentation, I will turn off my camera, and so you will see the whole screen of the presentation. So I would like to talk about optimizing lateral flow assay reagents, octet BLI for antibody-antigen characterization and QC today for you. Before we go into today's topic, I would like to shortly introduce you who we are. With more than 150 years history, Sartorius has over 60 locations worldwide. With 16,000 employees, we are happy to provide our customers with the right tools to achieve the pioneering technological breakthroughs. Sartorius offers strong strategic focus on the biopharma market with its two divisions, bioprocess solutions and lab products and service. Sartorius focus on the biopharmaceutical industry, offering solutions covering the entire biopharmaceutical value chain. The company supports its customers in increasing efficiency in drug development and simplifying production. Furthermore, Sartorius also offers solutions for lateral flow assays and IVD manufacturers. In today's webinar, following key learning lessons will be addressed. A short introduction of lateral flow assay and its design and consideration during the product development, an overview about octet BLI label-free systems and their application. Finally, I would like to show you how to use octet in optimization of lateral flow, including the antibody quality control and assay optimization. Let's have a look into lateral flow assay. Lateral flow tests are portable, easy to use in vitro medical devices. It is cost-efficient test and suitable for home testing. A lateral flow test consists of nitrocellulose membranes as key component and PES components. When we talk about the test performance of a lateral flow test, we expect to get the good performance in which the test shows clear background, true signals, high sensitivity and specificity, and at the same time to avoid the poor performance. In order to get the best performance of a lateral flow test, following optimization should be taken into consideration. During the product development for material optimization, nitrocellulose membrane, which used as the binding platform for antibody, PES components, and even backing cards, should be carefully selected. For optimization of reagents, the antibody on test line performing immunoreactions, conjugates, and buffers should be optimized during the production. Among these materials and reagents, the good quality of antibody and nitrocellulose membranes ensure the high quality of lateral flow test. In IVD industry, the quality of antibodies after production will be performed with several quality control steps. Besides protein concentration and isoelectric point, other control steps like immunoreactivity, cross-reactivity, purity, and homogeneity of antibodies, antibody-antigen interaction could be done by using octet BLI systems. Now I will give you an overview of octet BLI real-time label-free systems. During performing octet assays, you will get the binding specificity. Do molecules interact? Binding affinity, how strong is the binding? Binding kinetics, how fast is the interaction? And concentration analysis, how much analyte is there? Octet is a biosensor-based biomolecules interaction analysis platform, which is based on BLI technology. BLI is an optical technique that analyzes the interference pattern of white light reflected from two surfaces, a layer of immobilized proteins on biosensor tip and an internal reference layer. Any change in the number of molecules bound to the biosensor tip causes a shift in the interference pattern, in which is recorded in the real time. This real-time measurement can be used to calculate on and off rate by plotting binding rates against concentration. Sartorius offering the Octet R series provides a modular and scalable solution for molecular scanning in 96-well microplates. An Octet R2 system can be converted to an Octet R4 in the field, doubling your throughput instantly and offering the perfect balance between performance and price. You can even upgrade an Octet R8 to further increase throughput without the instrument ever leaving your lab. With high-throughput Octet systems, Octet RH16 and Octet RH96, you can accelerate discovery and get the maximal throughput. For example, the RH96 allows complete titer determinations for a 96-well plate of IgGs in just 2 minutes or provides 384 binding kinetics results in as little as 15 minutes. Only the differences in the microplate compatibility and sample volume, either Octet R series and Octet RH16 and RH96 systems, ensure the same instrument features to match the customer's needs. How does Octet support the optimization of lateral flow assay? The Octet system in lateral flow assay development supports the quality control of antibodies. Furthermore, it is also play an important role in assay development and assay optimization. Antibody quality can significantly affect the lateral flow assay performance. Both sensitivity and specificity of test results are calculated by the true results. The reduced occurrence of true results and an increase in false results will lead to reduced sensitivity and specificity of a lateral flow test. To get the best performance, high antibodies quality is required. Using Octet systems for performing antibodies quality control are in 3 steps. Firstly, Octet systems allow for evaluation of binding specificity between antibody and antigen. Here you can see 3 antibodies at normalized concentration were tested for their immunoreactivity of certain antigen. Antibodies 1 and 2 bonds to the immobilized antigen specifically, with antibody 1 showing a faster binding to antigen than antibody 2. Antibody 3 did not bind to the immobilized antigen, which is indicated by a flat, stable binding rate. The dose-response binding kinetics could be checked in the next step. With immobilized antigen on biosensor tip and titrate concentration series of 2 kinds of influenza A antibodies, we perform the binding kinetics assay. Both antibodies shows high binding affinities with antigens, which ensure the stable binding of antibody-antigen complex during the lateral flow. Type 1 antibodies shows higher binding on rate. It results in a faster test time, which is critical in time-sensitive test. The batch quality of antibodies is crucial for reproducible test results. Octet allows to compare the antibodies from different batches, which ensures the successive batches meet the specification. The test can be easily performed with immobilized antibodies on biosensor tips and titration series of antigen. Here, the sensogram shows that batch 1 antibodies meet the specification with a stable dissociation baseline. Batch 2 antibodies is out of specification since the sensogram shows an upward drifting dissociation indicative of non-specific binding. From these results, octet systems will help the developer knowing the binding specificity at the beginning of the process. The assay development will be more efficient and it will produce more reliable and robust test results. Octet will also support the developers knowing the binding kinetics and affinities of antibody to an antigen, leads to a robust and reproducible lateral flow assay. Furthermore, octet systems can be used to ensure the quality of incoming raw materials and monitor protein stability over multiple freeze and thaw cycles. To sum up, the benefits of octet system in antibodies quality control are ease of use, fast time to results, and octet will help you to accelerate product development. During the assay development, one of the most common questions would be which antibody should be printed on the CN membrane and which should be coupled with the nanoparticles. Here we firstly couple type 1 antibodies on nanoparticles and strip type 2 antibodies on the test line. Even at low antigen concentration and at high concentration, we could not get sufficient test line signals. However, if we change the order, that means couple type 2 antibodies on nanoparticles and strip type 1 on the test line. For both concentration, we could get the sufficient signals and clear background. To understand this behavior, we perform the antigen-antibody epitope binding in tandem assay. The antigens were immobilized on the biosensors. After reaching equilibrium, the biosensor was dipped into type 1 antibody solution, then type 2. A faster binding of antigen to the type 1 antibodies occurred, shows as steep curve, but only a minimal interaction with type 2 antibodies, which shows as a flat curve. This indicates that once antigens are bound to the type 1 antibody, the epitope for type 2 antibody might be inaccessible due to the steric hindrance. As a result, the binding occurred with a slow shift in the binding rate. This nicely explains the lateral flow test performance. The type 1 antibodies were coupled on the beads and bound to the antigen in the sample pads. Binding was fast and resulted in a stable antigen-antibody complex. Once the antigens bound to the type 1 antibody, the epitope for type 2 antibody was hardly accessible. The resulting sandwich formation occurred to a lesser extent and resulted in a weak signal, even at 10 times more antigen concentration. We performed the test at same condition to check the other situation. Here we dipped the biosensor tip, which immobilized with antigens into type 2 antibodies solution first, then in type 1. When the antigen first binds to the type 2 antibodies, it produces a slower and weaker interaction showed as a flat curve. When adding type 1 antibody, It binds to antigen faster and tighter, showing as a steep curve. If the antigen is bound to the type 2 antibody, which interacts slower and weaker than type 1, the epitope for type 1 antibody might be accessible. Consequently, the binding occurred with a significant shift in binding rate. Thus, in the test, the antigen was bound to the beads coupled with type 2 antibody. This binding was slower and weaker than that of type 1 antibody. Thus, the epitope for type 1 antibody was still accessible, resulting in an antibody-antigen complex with sufficient signal intensity. From these results, we could show that with octet systems, it is possible to screen for the appropriate binding partners and design an optimally performing lateral flow assay. Octet will help you save time for optimization, find answers with low consumption of materials, and to generate the best performance of your lateral flow assay. To sum up today's webinar, I want to emphasize that Sartorius supports customers to optimize the lateral flow assay with strong expertise and products. With our Unisat membranes and octet systems, will support our customers to generate the best performance of lateral flow assay. I hope you enjoyed today's webinar, and thank you for your attention.
Okay, first question we have. What epitope binning assay formats are supported on the octet and how do they differ?
Yes, this is actually a very good question. I think one of the biggest advantages of the octet instrument is that it can support all the three commonly known epitope binning formats. And this would include the in-tandem format, which is what Shuo has talked about in the webinar. And in this format, the antigen is first bound onto the biosensor surface and is then followed by a sequential binding of the antibody pairs being screened. So initially the primary antibody is bound, and then the secondary antibodies are then screened to see which ones bind to a different epitope. The second format would be the classical sandwich assay format, which is very well known by most folks within this environment. And in this format, the antibody is first immobilized or captured onto the biosensor surface, followed by the antigen binding, and finally the screening of the different secondary antibodies that are being characterized. And then the third format, which is less commonly known and which is a little bit more expensive than the first two formats, would be what's known as the premix format, where one antibody is initially premixed with the antigen. The antibody has to be in excess amounts to allow for a saturation of the epitope to which it binds. The mixture is then immobilized onto the biosensor surface, followed by the screening of the secondary antibodies in question.
Okay, thanks, David. The next question is, how does one select the most appropriate biosensor surface for antibody characterization on the octet? And which biosensor surface can be used in characterization of diagnostics reagent?
Yes, again, a very, very good question. So I think in general, it's important to note that for all ligand binding assays, that use systems or platforms similar to the octet, whether it is biolayer interferometry, which is the technology used on the octet, or whether it's surface plasmon resonance, the biosensor surface selection is probably the most critical part of the assay development. And this selection is typically based on the type of samples in question. So for example, if the samples being used are purified samples, typically streptavidin-based surfaces are the most appropriate, especially when the expected target binding is a high affinity binding. When, on the other hand, the samples are crude, so in other words, when there is lack of purified samples, then the streptavidin approach becomes very difficult to use because, the capture molecule would need to be bioattenuated, and this is not possible with a non-purified sample. As a result, a tag may be required, such as a hashtag or a GST tag may be needed depending on what assay orientation is needed. And it's also important to note that with crude samples, and especially if it's an antibody-based assay, similar to what we do with diagnostic reagents characterization, the antibody crude samples can be captured onto the biosensors that would utilize an antibody capture process, including anti-human capture or anti-mouse capture biosensors, protein A biosensors, or any biosensors that would typically target the Fc region of an antibody. When this approach is used, however, it is important to be able to assay develop in such a manner that the biosensor surface is blocked after the initial antibody loading step, especially when performing a sandwich format binning assay.
Okay, really, really interesting, David. Another question that is coming in, other than binning, how else might the octet be used in the reagent characterization in the diagnostics development field?
I will take this question. Thank you for the question. And one of the biggest advantages of octet instrument is its utility in rapid media screening for optimal conditions during assay development. This will not only help the developers to find out the optimal buffer for antibody immobilization, but also help them to optimize the pre-treatment of sample pairs, since not all antibodies are happy in one specific buffer system. The octet could be used for rapid buffer matrix screening affinity assays, where one analyte concentration is screened for binding in different matrix that may be spec'd with different excipients to determine optimal binding conditions. In addition, reference antibodies characterization could be stored and used for comparison with samples stored over time to monitor antibody stability, amongst other things.
Okay, thanks, Shuo. Really, really interesting. Yeah, then a question, I think this might be a question David could answer. Is there a recommended octet model for the diagnostic field?
Yes, another good question. I think I would say that all octet instruments, in fact, can be used within the diagnostic field. The difference, of course, would be the requirements for any given specific laboratory. The octet comes in multiple models with different configurations where the difference is mainly in throughput. So the technology in terms of the results obtained would be similar, but the throughput would be different. And the throughput range from 1 all the way to 96 samples. So in other words, there's an octet instrument that can run only one sample at a time, while the highest throughput instrument would run as many as 96 samples in tandem. Therefore, for laboratories that have low throughput needs, the octet N1 or the R2, which would run respectively 1 or 2 samples, would just be sufficient. However, if the throughput needs are significant, then users may consider using either the octet R8 that can run as many as 8 samples simultaneously, or RH16, 16 samples, or even the highest throughput instrument, the RH96, which would be capable for running as many as 96 samples in tandem.
Wow, this is really interesting and great to hear. Yeah, I see there is another question that is coming in. What is the minimum protein concentration needed to perform experiments on the octet?
Yes, again, a good question, but this one would depend obviously on 2 things. One, in terms of actual protein concentrations. The concentration for any given ligand binding assay is dependent on the affinity. So in other words, if you have a high affinity model pair, typically you'd require lower sample concentrations, whereas if you have a weak affinity pair, the sample concentrations needed are typically higher. But the other aspect of looking at sample concentrations would be in terms of sample volumes. And this depends on the instrument model in use. And this ranges from 4 microliters, for the N1 instrument, all the way to 40 microliters for the high throughput octet RH16, and RH96 instruments that utilize the 384 well plates. The octet R series, which includes the R2, the R4, and the R8, all utilize the 96 well plates. And in that case, they require 200 microliters in terms of sample volumes. So again, the concentrations will depend on affinity, but if you think in terms of sample volumes, those will depend on the instrument in use.
Okay, thanks, David. Yeah, the last question I can see here on the radar is the question, is it possible to measure aptamers on the octet, like protein DNA or protein RNA interactions?
Yes, again, another very good question. I think the way we look at a system like the octet, unlike fluidic-based systems, is that for so long as one of the binding partners can be immobilized onto a biosensor surface, there's a very good chance that, in fact, the interaction of the molecules can be analyzed. So in that regard, we have a lot of users who have done protein nucleic acid interactions, so protein DNA, protein RNA, which form part of the aptamers, are typically done on the instrument. Obviously, the assay development aspect of it depends on the scientific need that the user has, meaning that some optimization will need to be done. But in terms of the ability to be able to monitor the interaction, yes, certainly. The other key consideration for the octet, obviously, is molecular weight, purely based on the fact that it's a biolayer interferometry-based technology, where the molecular weight, the conformation, and the concentration, essentially the mass of the density of the biosensors, are critical. Other than that, for so long as the molecule can be immobilized, in fact, you should be able to measure the interactions.
Okay, thank you very much. So I think we are at the end of the Q&A session. So thanks, Shuo and David, for your time and answering all the great questions that are coming in from the audience.